Welcome to the deep dive.
Mm.
I'm genuinely thrilled you are joining us today because we are going on a journey into a piece of biological machinery that
It's
is
incredibly complex.
right, incredibly complex, astonishingly fast, and yet so completely invisible that you are using it right this very second without even registering it.
Yeah.
We are talking about the cognitive architecture operating inside your head every single time you speak, listen, read, or write.
Which you're doing right now.
Exactly. You are doing it right now just by processing the acoustic signals of my voice. So today, we are immersing ourselves in the fascinating field of psycholinguistics.
It's a hidden world, really, and frankly, one of the most computationally dense environments in the known universe. I mean, we tend to view language as this fluid, sort of organic human trait. We open our mouths and complex thoughts just materialize into the air.
Like magic.
Right, exactly. Or we scan a dense page of text and we instantly absorb the abstractions of someone who lived a century ago. But the sheer mechanical reality behind that?
The underlying gears turning.
Yes. The split-second biological, neurological, and cognitive operations required to pull that off, it represents a staggering feat of engineering.
To guide us through this architecture, we are looking at a stack of sources today. These are composed of academic course materials and structural overviews.
The heavy hitters.
Yeah, the foundational maps used to introduce the absolute core of psycholinguistics to researchers entering the field. They lay out the scope of the discipline, the primary methodological debates, and the fundamental questions regarding how our brains actually manage this hardware-software interface.
The overarching mission of these materials is to bridge a massive conceptual gap. For a long time, the study of language was strictly about knowing what language is on a structural, theoretical level.
Just the rules.
Exactly. But the mission of psycholinguistics, as outlined in our sources, is to shift that paradigm to understand how the brain actually executes it on a mechanical level. We are going to explore the mental lexicon.
The cognitive storage system in your head.
Right, and decode the split-second processing loops you execute effortlessly every day.
I want to ground this immediately with a metric from the sources that really contextualizes the scale of the problem here. When the sound waves from my voice hit your ear right now, it takes your brain less than half a second to translate those physical vibrations into an understanding of my semantic intent.
Less than 500 milliseconds.
Under 500 milliseconds. How is your brain finding the exact phonological matches, retrieving the semantic meanings out of tens of thousands of stored entries, and parsing the syntax, all in the literal blink of an eye?
That 500 millisecond window is the absolute crucible of psycholinguistics. In that fraction of a second, your auditory cortex processes the acoustic signal, your cognitive systems identify the phonemic boundaries, you access that mental lexicon to build words.
And it doesn't stop there.
No, then you arrange those words into a hierarchical syntactic structure, and you extract a global, pragmatic meaning based on your real-world context.
Unbelievable.
And the production end is equally daunting. Speaking a seemingly simple 2-second sentence requires selecting perhaps a dozen target lemmas out of a storage vault of tens of thousands and sequencing their motor articulation perfectly.
And you don't even think about it.
Never. You don't consciously search for them. The retrieval is entirely opaque to your conscious mind.
Okay, let's unpack this. To really grasp the magnitude of what psycholinguists are trying to reverse engineer, we need to establish the grand divide in the study of language. We need to distinguish between traditional linguistics and psycholinguistics.
A crucial distinction.
The sources emphasize that traditional linguistics functions essentially as the what. It's primarily a descriptive discipline.
Traditional linguistics aims to map the architecture of the system itself, completely independent of the biological machine running it. A traditional linguist is looking at the inventory of phonemes in a language, the morphological rules, the syntactic trees, the semantic boundaries.
They're cataloging dialects.
Cataloging dialects, speech styles, and historical language shifts. They provide the overarching taxonomy.
It is kind of like studying the rules of chess. The rules dictate how the knight moves, how the board is set up, and what constitutes a checkmate. The sources point out that linguistics gives us the necessary vocabulary to describe these structures accurately.
Right.
It allows us to catalog the typological similarities and differences between languages without making any value judgments about which language is better or worse. It treats language as a macro-level societal construct.
And that societal framing is the crucial differentiator here. Traditional linguistics views language as an external artifact shared by a community, but psycholinguistics pivots entirely to the how.
Right.
If linguistics is studying the rules of chess, psycholinguistics is studying the cognitive load, the memory retrieval, and the neural firing of the player sitting at the board actually making the moves.
The human element.
It is intensely process-oriented. It seeks to uncover the mental representations and the real-time cognitive processes involved in language use.
The sources make a sharp distinction regarding the perspective on the user here. While linguistics looks at society, psycholinguistics treats the language user as an individual organism. It is looking at the direct relationship between human cognitive hardware and linguistic output.
If we connect this to the bigger picture, psycholinguistics operates on the foundational assumption that our linguistic performance is entirely constrained and determined by the specific capabilities of the human mental apparatus.
Because we all share that same basic hardware.
Exactly. We all share highly conserved biological hardware. And because of that shared neurological architecture, psycholinguistics can trace universal patterns of cognitive behavior across massive populations.
So it doesn't matter what language you speak.
No. Whether you are processing Mandarin, Arabic, or English, the underlying cognitive bottlenecks, the memory limits, and the processing strategies show remarkable consistencies.
The container shapes the system. The specific configuration of human working memory, our pattern recognition algorithms, and our acoustic processing limitations directly dictate how human language is structured.
Precisely.
But if psycholinguistics is asking these radically different process-oriented questions, they can't just rely on the descriptive methodologies of traditional linguistics. You can't just observe a conversation and map a dialect.
You certainly cannot, and you cannot rely on introspection either.
Right, I can't just ask you how you did it.
Exactly. You can't ask a subject, how did you retrieve the lemma for apple instead of orange just now? The subject has zero conscious access to that retrieval process.
It's totally subconscious.
Therefore, the methodology has to shift to highly controlled laboratory observations and behavioral experiments. Psycholinguists have to design experimental paradigms that catch the brain in the act of processing.
We're talking about breaking into a highly skilled, fully automated performance. It is like trying to analyze the individual muscle twitches of a concert pianist while they're playing a Chopin etude at full speed.
That's a great analogy. To do that, researchers rely on chronometric data measuring reaction times down to the millisecond.
Yeah.
They use techniques like eye tracking to see exactly where a reader's gaze fixates on a syntactically ambiguous word. Or they use EEG to measure the electrical event-related potentials, like the N400 wave, which spikes precisely when the brain encounters a semantic anomaly.
So they're literally watching the brain react in real time.
They are forcing the brain to process carefully manipulated stimuli to see where the system hesitates, where it speeds up, or where it crashes.
Here's where it gets really interesting. Let's look at what they're actually trying to measure with these intense laboratory setups. The sources dive heavily into the architecture of the mental lexicon.
The storage vault.
Exactly. We have tens of thousands of words stored in our heads. The sheer volume is one thing, but the organizational principles are what dictate that sub-500 millisecond retrieval speed. How is this lexicon actually organized?
The organizational architecture is one of the most fiercely debated topics in the field. When you're dealing with a database of 50 to 100,000 items, a sequential search is biologically impossible given the time constraints of fluid conversation.
Right, if you had to start at A and go to Z every time.
Exactly. If the lexicon were organized alphabetically like a printed dictionary, finding a word starting with Z would take measurably longer than finding a word starting with A.
And we know that's not true.
We know from behavioral data that this doesn't happen, so the system must be highly interconnected, perhaps conceptually, more like a multidimensional thesaurus.
The sources use the word cat to illustrate this mapping problem. Where exactly does the representation for cat live in your cognitive filing system? Is it clustered in a phonological neighborhood alongside words that share its acoustic onset, like catch, cap, and cattle?
That's one theory.
Or is it embedded in a semantic network, physically or conceptually linked to meaning-related nodes like dog, mouse, and feline? Or does the brain utilize a hybrid architecture?
The behavioral evidence strongly points to a hybrid system, but semantic networks are incredibly dominant. We see this through experimental paradigms like semantic priming.
How does that work?
Well, if a researcher flashes the word dog on a screen for a few milliseconds before flashing the word cat, subjects will recognize cat as a real word significantly faster than if they had been primed with an unrelated word like table.
Oh, that's fascinating.
This implies a spreading activation model. Accessing the node for dog sends residual activation through the network to related concepts, pre-warming the node for cat so it is ready for faster retrieval.
Pre-warming the node, I love that. But the phonological clustering must exist too, right? If the system was purely semantic, we wouldn't experience tip-of-the-tongue states where we can recall that a word starts with an S and has 3 syllables, but we just can't access its meaning.
That is a highly astute observation. Tip-of-the-tongue phenomena strongly support the idea that the mental lexicon has distinct, separable layers.
Okay.
There is a conceptual semantic layer where the abstract meaning lives, and a distinct phonological layer where the actual sound forms, the lexemes, are stored. Sometimes the connection between the concept and the sound form temporarily degrades or gets blocked.
That is so frustrating when it happens.
But the architectural questions go even deeper than word associations. We have to look at the micro level of phonemic representation.
Right. The sources ask a critical question about the granularity of this storage. When your auditory system processes the word cat, are you recognizing the component phonemes sequentially? Do you identify the K sound, hold it in working memory, identify the A sound, then the T sound, and then synthesize them into the lexical entry?
That sounds exhausting.
It does. Or do you process the entire acoustic envelope of the word in parallel as a single holistic burst of information?
If we relied on strict sequential parsing of every single phoneme, spoken language comprehension would likely collapse under its own processing weight, especially in rapid, continuous speech where phonemes smear together through co-articulation.
Because we don't speak in perfect, isolated sounds.
Exactly. Models like the cohort theory suggest that as soon as you hear the initial K sound, your brain instantly activates every single word in your lexicon that begins with that sound, the entire cohort of candidates.
Thousands of words all at once.
Yes. And then as the A sound arrives, the cohort rapidly shrinks, eliminating words like cop or keep, until only cat remains. It is an active, parallel process of elimination happening in real time.
Which means the brain is constantly predicting the future based on milliseconds of acoustic data. But the storage problem becomes even more complex when we move beyond simple monomorphemic words and look at morphological storage.
The complex words.
Yes, this is what the sources refer to as the government debate. How do we store complex multimorpheme words?
This is the battle between the full listing hypothesis and the affix stripping hypothesis. Does your lexicon contain a single pre-packaged entry for the word government? Or does your cognitive architecture prioritize storage space by only storing the root morpheme govern and a separate list of bound morphemes like biment, est, and esk, and eng?
So if you only store the root and the suffixes, you are saving a massive amount of cognitive hard drive space. You don't need separate entries for govern, governs, govern, governing, and government. Your lexicon is incredibly lean. But the trade-off is computational cost. Your brain has to actively assemble govern and mement on the fly every single time you want to use the word.
And conversely, if you pre-store every single morphological variation as its own discrete entry, retrieval is theoretically instantaneous because no assembly is required. But the storage demands become astronomical.
So which one is it?
The current consensus in psycholinguistics leans toward a dual route model. Highly frequent complex words, words we use constantly, might achieve full listing status because the brain decides it is more efficient to memorize them than to compute them every time.
That makes sense.
But less frequent words are likely assembled and disassembled via morphological rules.
This friction between rules versus storage is perfectly illustrated in the sources by the plural problem. Think about pluralization. For regular nouns, the rule-based system seems obvious. You take a novel word, say wug, and if I tell you there are 2 of them, you instantly know they are wugs.
You didn't have wugs stored in your lexicon, you just applied the morphological rule.
Exactly. The application of that rule is a generative cognitive process. But the system encounters a major bottleneck when dealing with irregular forms.
Right, the exceptions.
How does the rule-based model account for a word like children or mice? You cannot apply the standard pluralization rule to child to generate children. Child's is a morphological error that we typically only see in early childhood language acquisition.
This raises an important question. Do irregular forms like children require their own distinct, hard-coded storage space in the lexicon precisely because they defy the computational rules?
It seems like they'd have to.
Are we running a dual system architecture where a rule-based assembly line handles the regular majority while a rote memorization vault handles the irregular exception?
What does the data say?
The behavioral evidence from psycholinguistic studies on reaction times heavily supports this dual system view. When subjects are asked to produce the past tense of a regular verb, the reaction time suggests active computation. When asked to produce the past tense of an irregular verb, the reaction time suggests direct lexical retrieval.
Wow, so we actually switch strategies mid-sentence.
It demonstrates that the brain is highly pragmatic. It employs whichever cognitive strategy, computation, or retrieval is most efficient for the specific linguistic item at hand.
It is a phenomenal optimization of resources. And this transitions perfectly into the next major theme of our sources, the need for speed.
A very fitting title.
We are moving from the static architecture of the lexicon to the dynamic, real-time processing of language in action. Let's examine comprehension theory.
What's fascinating here is we noted earlier the under 500 millisecond window for comprehension, but the mechanics of that window are what psycholinguists really obsess over.
It's a huge puzzle.
When sound waves hit your tympanic membrane, the brain doesn't just passively receive a completed message. Comprehension is a highly active, constructive process. The sources ask how we build a global meaning representation from the incoming signal.
Because the acoustic signal itself is incredibly impoverished, right? It is just a continuous stream of frequencies. The brain has to segment that stream, identify the phones, retrieve the words, and then parse the syntax.
Exactly.
But words and syntax are just empty vessels without semantic context. If you hear the sentence, "The man saw the spy with binoculars," the syntax alone cannot tell you who actually has the binoculars.
That is a classic structural ambiguity. Does the prepositional phrase "with the binoculars" modify the verb saw, meaning the man used binoculars to see the spy? Or does it modify the noun spy, meaning the man saw a spy who happened to be carrying binoculars?
Right.
The psycholinguistic question is, how and when does the brain resolve this ambiguity? Does it build a purely syntactic tree first, realize it is ambiguous, and then consult real-world knowledge? Or does semantic knowledge interact with syntactic parsing instantaneously, guiding the structural build from the very first millisecond?
The eye-tracking data on reading these types of ambiguous sentences is just fascinating. When people read so-called garden path sentences structured to trick the reader into an incorrect syntactic parse, like "the horse raced past the barn fell," their eyes physically regress.
Did you?
They read smoothly until they hit the word "fell," realize their initial syntactic tree was wrong, and their eyes dart back to the beginning of the sentence to reparse it.
Those saccadic regressions prove that the brain is processing language incrementally. We don't wait until the end of a sentence to figure out the structure or the meaning. We build the mental model word by word, constantly updating our hypotheses about the speaker's intent.
So we are essentially guessing as we go.
Comprehension is not just decoding, it is actively predicting the incoming linguistic stream based on deep real-world knowledge and statistical probabilities.
And if comprehension is a high-speed predictive modeling system, production theory, the act of generating an utterance from scratch, is an entirely different beast.
Oh, absolutely.
How do we take a non-linguistic, abstract conceptual thought and convert it into a highly structured, sequential string of articulated sounds?
The sheer cognitive load of speech production is immense. When you formulate a sentence, you are navigating what psycholinguists call the great sequencing debate. The core debate, as highlighted in the sources, centers on the order of operations. What is the very first step in constructing an utterance?
Do we generate an abstract, empty syntactic frame first? Do we decide, I'm going to use a passive structure, noun phrase followed by a verb phrase, and only then go digging into the mental lexicon to find specific words to plug into those empty slots?
That is the structure-driven model. Or do we operate via a lexically driven model? Do we access the core semantic lemmas first, the key concepts we desperately want to communicate, and then rely on the grammatical properties inherent to those specific words to dictate the syntactic structure of the sentence?
It is the architectural equivalent of asking whether you build the steel frame of a skyscraper first and then choose the windows, or whether the specific type of windows you choose dictates how the steel frame must be built.
That's a perfect way to visualize it. Most modern psycholinguistic models of production, like Levelt's model, suggest a highly staged process.
Okay, walk us through that.
It begins with conceptualization, deciding what to say. Then formulation, where you retrieve the lemmas and build the syntactic frame almost simultaneously, followed by phonological encoding, where you retrieve the actual sounds of the words, and finally articulation, where the motor cortex commands the vocal tract.
All in the span of milliseconds.
The fact that this entire cascade happens in milliseconds without conscious oversight is the central marvel of the field.
The sources also raise the concept of the comprehension production loop. Are these two systems, the one parsing incoming speech and the one generating outgoing speech, completely isolated modules in the brain? Or do they share cognitive architecture?
This is a bleeding-edge area of research right now. How much does our production system inform our comprehension?
Right.
There are theories suggesting that when we listen to someone speak, we use our own internal motor production system to subtly simulate their articulatory gestures. We essentially subvocally shadow them to help parse the acoustic signal.
We are mirroring them in our own heads.
Exactly. We might use the very same syntactic building mechanisms to decode their sentences that we use to encode our own. The systems are deeply interwoven.
So what does this all mean when we look under the hood? All of these theoretical models,
Yeah.
the semantic networks, the incremental parsers, the dual route morphological systems, must map onto biological tissue.
I have to live somewhere physical.
This brings us to the next critical section outlined in the sources: neurology, biology, and exceptional circumstances.
Moving from the abstract cognitive architecture to the neurobiological reality is essential here. Psycholinguistics heavily relies on neuroimaging techniques to determine where the brain physically executes these functions. While the old phrenological idea of finding a single cat neuron is obsolete, we do see massive regional specializations.
We have classic localizations like Broca's area in the frontal lobe, historically associated with speech production and syntactic processing, and Wernicke's area in the temporal lobe, associated with language comprehension and semantic processing. But the modern neurobiological models, the sources allude to, go way beyond these two isolated islands.
Yes, contemporary models view language processing as relying on massive distributed networks. For instance, the dual-stream model of speech processing suggests a dorsal stream that maps acoustic speech signals to frontal lobe articulatory networks, essentially linking sound to action. And a ventral stream that maps acoustic signals to temporal lobe conceptual networks, linking sound to meaning. It is a highly parallel, interconnected neurological web.
And this neurobiological framing forces us to confront evolutionary questions. The sources explicitly ask how differences in the human brain account for our species' unique development of language. What specific tweaks to our neurological hardware allowed us to manipulate syntax when other highly intelligent primates cannot?
That directly informs the study of first language acquisition. How do infants acquire this massively complex system so rapidly without explicit instruction? The progression infants go through, from babbling to single words to telegraphic speech to complex syntax, is remarkably consistent across cultures.
It happens everywhere, in every language.
This predictable developmental trajectory strongly points to the question of innate ability.
The classic Chomskyan debate. Are we born with a biological blueprint, a universal grammar, hardwired into our neurology, just waiting for environmental input to set the specific parameters for English or Arabic?
Yeah.
The speed of acquisition, despite the poverty of the stimulus, the fact that children don't hear enough perfectly formed sentences to logically deduce all the complex rules of grammar, is a massive piece of the psycholinguistic puzzle.
To truly test the resilience and nature of this biological faculty, the sources mandate that researchers examine exceptional circumstances. We learn an immense amount about typical language processing by observing the system when it operates atypically.
Why do some children, despite normal intelligence and adequate environmental input, develop specific language impairments or conditions like dyslexia? If language is hardwired, where's the variance coming from?
This raises an important question, especially with dyslexia, which is a profound window into processing. The prevailing psycholinguistic theory is not that it is a visual deficit seeing letters backward.
Right, that's a common misconception.
It's rather a phonological processing deficit. The brain struggles to efficiently map the visual graphemes, the letters on the page, onto the corresponding phonological representations in the mental lexicon. By pinpointing exactly where the reading process degrades in dyslexia, researchers reverse engineer the precise mechanisms required for fluent decoding in typical readers.
The sources also point to brain damage as a critical investigative tool. When a patient suffers a localized lesion, perhaps from a stroke, they might exhibit specific aphasias. A patient with Broca's aphasia might completely lose the ability to deploy syntax, speaking in halting, ungrammatical nouns, yet their semantic comprehension remains largely intact.
Conversely, a patient with Wernicke's aphasia might produce fluid, syntactically perfect sentences that are entirely devoid of semantic meaning, a kind of fluent word salad.
It's tragic, but illuminating.
This double dissociation provides ironclad biological proof that syntax and semantics are handled by functionally distinct neural networks. We map the machine by analyzing exactly how it breaks down.
It is a clinical approach, but as the sources indicate, it serves a much larger, unifying objective. This brings us to the ultimate goal of psycholinguistics. The field isn't just about cataloging reaction times or mapping localized brain lesions. It has a profound philosophical core.
The sources articulate this dual mandate clearly. The primary immediate goal is to establish a rigorous, empirically backed understanding of the mechanistic processes underlying language. We want the full blueprints of the cognitive machine.
Wow.
But the secondary ultimate goal is to view language not just as a communicative utility, but as a direct, observable product of the human mind itself.
Language is the most transparent window we have into human cognition. The way we structure our sentences provides direct evidence of the way we organize our thoughts. Our daily sensory experience of the reality around us is essentially a chaotic barrage of continuous stimuli. Language provides the cognitive scaffolding we use to impose patterns upon that chaos.
We use syntax to define the relationships between entities, who did what to whom. We use semantics to categorize the infinite variety of the physical world into discrete, manageable concepts. We use tense to organize our perception of time and causality.
It's how we make sense of reality.
By studying the mechanics of psycholinguistics, we are fundamentally studying the architecture of human thought.
Which explains why the scope of this field, as laid out in the introductory course materials, is so dauntingly vast. To understand this machine, a psycholinguist must integrate neurobiology to understand the hardware, acoustics to understand the input, cognitive psychology to understand the memory architecture, and theoretical linguistics to understand the structural rules.
It's a massive undertaking.
They have to synthesize speech perception, sentence processing, language acquisition, and the decoding of orthography and reading. It is the ultimate interdisciplinary science.
It is an attempt to map the cognitive operating system of the human species. Every experimental paradigm, every millisecond of reaction time recorded, is a step toward understanding how biology generates meaning.
That brings us perfectly back to you, the listener. The next time you fire off a text message while walking down the street, or you effortlessly follow a complex argument in a deep dive like this one, I want you to appreciate the staggering computational power your mental apparatus is executing in the background.
It's worth pausing to think about.
In the span of a few milliseconds, you are navigating a lexicon of tens of thousands of entries, assembling complex hierarchical structures and decoding acoustic signals with a precision that outpaces our most advanced supercomputers. It is a biological miracle occurring seamlessly inside your head.
And this raises a final thought to mull over, building on the realization that human language is strictly constrained by human neurobiology. If our concept of words, syntax, and meaning is entirely dependent on the specific memory limits and processing speeds of our biological brains, what happens when we encounter a non-human intelligence?
That's a wild thought.
Consider an advanced artificial general intelligence, or even a hypothetical extraterrestrial mind. If their cognitive architecture lacks our biological constraints, if they possess infinite working memory and instantaneous parallel processing, would they even utilize discrete words or linear syntax?
Or would it just be pure data transfer?
Exactly. Or would their communicative output be a multidimensional exchange of raw, uncompressed semantic data, fundamentally unrecognizable as language to the human mind?
If the architecture of the mind dictates the structure of the language, an alien architecture guarantees an entirely alien linguistics. That is a brilliant thought to chew on. Thank you for joining us on this exploration of the invisible machinery inside your own head. Keep questioning the everyday complexity around you, and we'll see you on the next deep dive.